So this is problem 8.109 that we went over in class today that we had a little trouble with. So finding the empirical formula first, we're taking the percentages, bringing those percentages directly to grams, and now we find in doing that we have 2.17 moles of each, and that the empirical formula should be SN or NS. It doesn't matter at this point what the order is. So the mass of the empirical formula, or the empirical formula mass, you can calculate that, 32.06 plus 14.01, and you get 46.07. Given in the problem is the molecular formula mass, 184.3, and 184.3 divided by 46.07 gives you about 4. Remember, those are going to be nice whole numbers, and if they're anything but that, go back and check your empirical formula because something went very wrong. And so with that ratio of 4 to 1, we know that it's got to be S4, N4. So part B now asks, write the Lewis structure for the molecule. When you start adding up valence electrons, you find that there are 40 of them. And so we're going to alternate the sulfur and nitrogen in a ring pattern as implied in the problem. In part C, where it says predict the bond distances between the atoms in the ring. But we'll get to part C in a minute. So the only way to make this work and use all 40 electrons and have everybody satisfying the octet rule is to alternate single and double bonds. That's a little weird, but let's set that weirdness aside for a minute and just assume that this is correct. Every one of those atoms is going to have another pair of electrons on it, and so that uses all 40 of those electrons. So now comes the challenging part. We're trying to predict the bond distance for the atoms. And we've got to pull some information, some from the average bond lengths table, table 8.5, and maybe some from the atomic radius table. If we look at the typical nitrogen to nitrogen single bond, it has a length of 1.47. So that would give an approximate radius for each atom of 0.735 angstroms. The nitrogen to nitrogen double bond is about 1.24. And so about 0.62 would be kind of the bonding radius for those. We're told in the problem that the sulfur to sulfur bond length is 2.05, so half of that's roughly 1.03 angstroms. Now if we're assuming a single bond to nitrogen and sulfur, we get a 1.77 angstrom bond length as maybe the typical. But if we look at the nitrogen and sulfur, right, 0.62 and what? Well, we got to start looking and making some assumptions in this table. Let's assume, just for the sake of argument, that since the nitrogen single bond length and the nitrogen double bond length, right, those bonding radius is decreased by about 0.115, let's assume that sulfur does the same thing. And so if that's the case, we get about a 0.92 bonding radius for the sulfur to sulfur double bond. And so if we put those two together in a nitrogen to sulfur bond, we get about 1.54 angstroms. Now I think there's a lot of assumptions in here. Should probably count up the number of times I've said that. And so we know that it's resonance, and we know that the bond isn't a typical single bond length, and it's not a typical double bond length. It should be somewhere in between. So we look at the answer choices that were given in the problem, and the only one based on all of those assumptions that makes sense is 1.60 to 1.65 angstroms. We could estimate the approximate bond length based on the radius of the sulfur atom and the nitrogen atom, and when we do that we get something like 1.76, so that's pretty close. We know it's got to be less than 1.76, and so based on that alone, just from the radius table, we can cross off the bottom three choices. And then we are left to kind of struggle through and make the assumptions that it's not going to be 1.5 to 1.55, but that the 1.60 to 1.65 is the better choice. So in this last part, where we're estimating the average bond enthalpy in the compound, we've got to get a little technical and a little formal here in terms of our definitions and the equations we're looking at. So if we're taking this compound and breaking the bonds, that means we're breaking it into sulfur gas and nitrogen gas. And so to find the heat of reaction for this, we can simply use the heats of formation. We're told that the heat of formation for the reactants 480, and for sulfur gas is 222.8, and we have to look up the heat of formation for nitrogen gas. And once we do that, we can find the heat of reaction. And that heat of reaction will be the amount of heat needed to break those bonds. And so once we plug in here sum of the heats of formation of the products minus the sum of the heats of formation of the reactants, we're going to get 2,302 as the overall heat of reaction here. And again, remember, that's the amount of heat needed then to break those bonds. And by breaking those bonds, again, we're separating the sulfur and nitrogen so far apart from each other that they're no longer attracted to each other. That's why we have to use sulfur gas and nitrogen gas. Now, how many bonds did we break per mole of S4N4? Well, we broke 8 bonds per mole. Go back to the Lewis structure that you wrote in the beginning of this problem, and you'll see that there are those 4 bonds. So 2302 divided by 8 should give you, I think we said 287 or something like that, but let me do the calculation now. 287 or 288 kilojoules per mole, and that's the average bond enthalpy.